All right, so in 12.3, we talked about the dot product, which is a way of multiplying two vectors. And I had alluded to the fact that there's two different ways that we can form products of vectors, one of which we talked about in 12.3, the dot product, and one of which we're going to talk about now, the cross product. However, before we can talk about the cross product, it's going to be helpful to review a little bit on matrices and determinants. This is usually something that you talk about in pre-calculus, sometimes even intermediate algebra. These ideas are introduced. And then if you've taken linear algebra, you know far more about matrices and determinants than we need for this class. But we're going to just go over the bare bones basics of what we need to do in this section. So just quickly here, a matrix, for our purposes, we can think of as a rectangular array of numbers. The individual numbers within a matrix are called entries, and we can single out within any matrix its rows or its columns, like this. Now, what we're going to be focusing on primarily are 3 by 3 matrices, which means 3 rows, 3 columns. However, we're going to be breaking these down into 2 by 2 matrices as well, so 2 rows, 2 columns. Now, there's an operation that you can perform on a matrix as long as the matrix is what we call square, which means it has the same number of rows as columns, and it's called a determinant. We only need to be able to take determinants of 3 by 3 and 2 by 2 matrices, but it does apply to n by n matrices as well. That's a topic for linear algebra. So let's start by defining what the determinant of a 2 by 2 matrix is. Here's a little 2 by 2 matrix, A, B, C, D, and I want to call attention to the difference in notation here. It might be a little bit difficult to spot, but here, when we're just talking about a matrix, the borders of this matrix are essentially these big square brackets. When we want to talk about the determinant of a matrix, it's just vertical lines, almost like an absolute value sign. So these vertical lines indicate that we're taking the determinant of the matrix with entries A, B, C, D. Okay? The way that we evaluate the determinant of a 2 by 2 matrix is it's equal to a scalar, AD minus BC. Notice that's the product of these diagonal entries here. We call the top left to bottom right diagonal the main diagonal. And then we subtract the product of these entries on the other diagonal. So AD minus BC. That's how we evaluate a 2 by 2 determinant. And again, it's very important to note that the result of a determinant is not another matrix. It's a scalar. It's a real number. Okay? Now, we need the idea of a 2 by 2 matrix or a determinant because it shows up in the way that we evaluate a 3 by 3 determinant. And this is not the only way to do a 3 by 3 determinant. Some of you may have learned this technique for rewriting the first 2 columns here and then doing these diagonals and adding and subtracting a bunch of products. That's fine, but I'm only going to be using this approach for 3 by 3 determinants in this section. So the idea of a 3 by 3 determinant is we break it down into a sum of specific entries from the matrix times 2 by 2 matrices that also come from that matrix. Now, you don't want to memorize this. This looks really, really complicated. Instead, you want to see this for what it is in the original matrix. So first of all, notice that these scalars here, A11, A12, and A13, those are exactly the first 3 entries in this row. Okay? Now, for this first term, I'm taking the entry A11, it's showing up here, and I'm multiplying it to a 2 by 2 determinant. And that 2 by 2 determinant occurs or the way that I find it is I go to where I picked the entry, A11, and I delete the column and row that it appears in. The resulting 2 by 2 determinant, or 2 by 2 matrix, is what I'm taking the determinant of right here. So again, take A11, stick it here, block out its column and row that it appears in, and the remaining terms create a 2 by 2 determinant that it gets multiplied to. Then we go on to the next entry in that first row, A12, and this becomes a minus here. So we're subtracting whatever this term is, and once again, we block out the column and row that it appears in, and the remaining 4 terms go together to create a 2 by 2 determinant. Finally, we do the same thing with the last entry, but this time we end up with a plus. We put the entry down, and then we block out the column and row, create a 2 by 2 determinant out of what entries remain there. Okay, this may seem like an incredibly bizarre way to define an operation on a matrix. It may seem like the just kind of seemingly arbitrary way of coming up with this value, whatever this turns out to be, couldn't possibly have any relevance anywhere. But it turns out the determinant is an incredibly useful operation that we can perform on matrices, and we can extract all kinds of information out of it. Unfortunately, we only get to see a little bit of that in this class. The real study of matrices and determinants is handled in linear algebra. So if you're taking linear algebra either now or in the future, then you'll be able to see in much more depth exactly what the determinant is, and hopefully it'll help you make sense of why it's defined this way. For us, though, we just need to know how to compute these things. So here's a 3 by 3 determinant. We want to evaluate this. I'm going to expand along this first row. I mentioned here that this technique is called cofactor expansion along the first row. So this is equal to the first entry, 1, times the 2 by 2 determinant that I would get from deleting the first column and first row. 3, -4, 0, 5. Then I subtract the next entry, 0, times the 2 by 2 determinant that I would get by blocking out its column and row. That's 2, 1, -4, 5. Finally, I add the last term, -4, times the 2 by 2 determinant with entries 2, 1, and 3, and 0. 2, 1, 3, 0. Okay? Now, this becomes 1 times 3 times 5 minus -4 times 0. That's the determinant of this 2 by 2, which we defined up above. We said that it's the product of the main diagonal entries minus the product of the other diagonal entries. That's what we have here. This guy I'm not even going to bother with, because no matter what this determinant comes out to, it's just being multiplied by 0, so it's going to 0 out and disappear on us anyways. This becomes -4 times 2 times 0 minus 3 times 1. And so simplifying all of this down, doing the arithmetic, we should end up with 27. A couple of things worth mentioning here. One, again, just to reiterate, the determinant of the matrix is a real number, not another matrix. Okay, so it's a scalar. Secondly, I called this cofactor expansion along the first row. It turns out that we can expand a determinant the way that we did here, use this thing called cofactor expansion along any row that we want, and along any column that we want. And what will be slightly different depending on what column or row you choose is where these pluses and minuses appear. But aside from that, the determinant will always come out to the same thing no matter what row or what column you expand along. And the reason for that, again, is something that's dealt with in linear algebra. And also, for our purposes, we're never going to expand along anything except for the first row. Okay? Last thing I want to mention about this, I went through this step by step, but pretty much all of the determinants that I evaluate from here forward, I'm not going to write down this much detail for. In fact, I may even just jump straight to an answer from here on forward, because technically this is supposed to be review anyways. So you should be able to fill in those gaps. But let's see what we actually need the determinant for. So here's where we define this thing called the cross product. Cross products are only defined for vectors in R3. Vectors with 3 components. You cannot take the cross product of vectors from R2 or R4 or R100 or any of the other spaces out there. It's strictly for 3-dimensional vectors. If you have 2 3-dimensional vectors, A and B, we define the cross product this way. Notice the top row of this determinant here is exactly the standard basis vectors in R3. I, J, K. The second row contains the entries, or sorry, the components of A in order, A1, A2, and A3. The last row contains the components of B in order, B1, B2, B3. This, if you evaluate this determinant, will produce a vector, as we'll see in an example, and that vector is what we call the cross product. So, let's practice this. I want to evaluate the cross product of these two vectors. Well, the cross product is going to look like I, J, K, negative 2, 1, 4, 0, 5, negative 3. So what is this? Well, because I'm expanding along the first row, I'm going to be doing the vector I times this 2 by 2 determinant. 1, 4, 5, negative 3. I'm going to put I on this side. Okay, and then we're going to subtract J times the 2 by 2 determinant, negative 2, 0, 4, negative 3. Don't forget that in expanding along the first row, we need a minus here, then a plus here. Negative 2, 0, 1, 5. That would be this 2 by 2 right here. And that gives me K. Now, if I were to evaluate each of these determinants, which I'm not going to show you all the steps for, we're going to go straight to an answer. We're going to get negative 23I minus 6J minus 10K. That's a vector. It's not a scalar because it's got these standard basis vectors in it. In fact, if I wanted to, I could write it in component form as negative 23, negative 6, negative 10. Either of these are an acceptable way to write that answer. Okay? So, that's what the cross product looks like when we evaluate it. But why would you bother doing that? What's the point of taking a cross product this way? It has to have some sort of relevance somewhere for us to be spending time on it, right? Well, this first theorem here sort of illustrates its primary purpose. The vector that we obtain by taking the cross product of two vectors, A and B, is always orthogonal to both vectors at the same time, A and B. Now, how would I establish that? Well, again, if we let A and B be vectors in R3 with components A1, A2, A3, and B1, B2, B3, like we did previously, to verify that we usually just read this as A cross B. To verify that the vector A cross B is orthogonal to both of these, I have to evaluate two different dot products. Remember, the dot product of two vectors, if it's equal to 0, is how we determine whether or not something is, two vectors are orthogonal. So I'm going to start by taking the dot product of A cross B with the vector A to first show that these two vectors are orthogonal. Now, I'm going to skip a lengthy discussion about all of this work, and instead I'm going to let you look at the steps to convince yourself that this is true. But think about this for a moment. These determinants right here, these would be the components of this vector. That's what happened up here. Negative 23 is what this determinant was equal to. Negative 6 is what this determinant, after applying that minus to it, came out to. So these determinants become the components of our vector. And how do you evaluate a dot product? You take the components of this vector, multiply them to the corresponding components of this vector, A1, A2, and A3, and then you sum the results. So that's where this is coming from. Then what happens is we evaluate each of these determinants, and that's where things start to get really, really messy. Each determinant produces a difference, as we're seeing here, which we'll have to distribute the A1, A2, and A3 into. And then it becomes this big giant mess. But if you notice, there's 6 terms here. And if you look carefully, you're going to find that we can pair up like terms so that everything cancels out and becomes 0. And I'll let you investigate that and make sure that that's true just by looking at this. But ultimately what that told us is that the dot product of A with A cross B was 0, meaning A cross B and A are both orthogonal. We could repeat this process by putting a B here instead of an A, and the same thing would happen. So that proves this. And that's really, really useful because regardless of what A and B are, taking the cross product of A with B always gives us a vector that's orthogonal to both at the same time. That's something that we need to be able to do starting in section 12.5 when we find equations for planes and things like that. Okay. Now the cross product obeys something that we call the right-hand rule. So the right-hand rule basically works this way. If you use your right hand, there's kind of a picture of it right here, and you point your fingers in the direction of A, which is going to be the vector that appears first in the cross product, and then you curl your fingers in the direction of B, so kind of along this angle theta right here. Whichever direction your thumb is pointing is the direction that A cross B will be appearing. So note if we tried to reverse the direction here, if I try to do B cross A instead of A cross B, in order for me to do this, I'd have to flip my hand upside down, which is hard to see on my camera right now, to have my fingers point in the direction of B and also curl my fingers along theta to get to A. That would imply that B cross A points down where A cross B points up relative to each other. That's important because it also shows that the cross product is not commutative. A cross B and B cross A are not necessarily equal to each other. And we'll see that again in a minute. Okay. So let's do a little bit more here. This is a very algebra-heavy proof, and it's admittedly kind of a difficult one to see how they would have jumped from one step to the next, but you can verify that it works. Let me point out what I'm talking about here in a minute. So let's suppose theta is the angle between vectors A and B. And remember, as we said before, theta would be between 0 and pi radians, or 0 and 180 degrees. Then, if we took the magnitude of the cross product, it's going to equal the product of the magnitudes of A and B times the sine of the angle theta between them. Okay, now this proof, like I said, is very algebra heavy and it uses a little bit of trig in there. But one thing I want to point out is this looks very similar to something that we showed with the dot product. Remember, we showed that A dot B is equal to the product of the magnitudes of those vectors times the cosine of theta. With the cross product, two things are different. It's sine instead of cosine. And because this wouldn't make any sense if this side was a vector, because this side is a scalar, we need magnitude bars here. We need to show that we're talking about the magnitude of A cross B, not just A cross B itself. All right? So here what we're doing is instead of looking at the magnitude of A cross B by itself, we're squaring it. And the reason for that is because that eliminates the gigantic square root that you'd have to be dealing with when evaluating the magnitude of that vector. But you can see it's a sum of the squares of the components of that cross product. If you go through and square each of these guys, you get this really, really long, messy, horrendous algebraic expression. And then, this is straight out of your book, your author jumps straight from this step to this step where some things have been factored, and it's really, really difficult to see how you ever would have arrived at this step from this one. There's some very clever algebra taking us from here to here, and it's not meant to be obvious. But if you doubted it, you could go back a step. You can multiply these trinomials out, and then you can square this trinomial, combine all of these like terms, and you should get right back to this, okay? So it works, it's just not obvious how we would have gotten there. Now, why did things get factored this way? Well, notice what we have in this set of parentheses. It's the sum of the squares of the components of A, and here, this is the sum of the squares of the components of B. And they're being multiplied. That's the same thing as the magnitude of A squared times the magnitude of B squared. Similarly, if we look within here, A1 times B1 plus A2 times B2 plus A3 times B3, that's exactly what you would have gotten if you took the dot product of A with B. And that's being squared as well. We can see that happening. Okay? Now, what we're going to do is use our dot product definition that involves the cosine of the angle between them. Remember, like we said before, the dot product of A with B is the product of the magnitudes of A and B times the cosine of the angle between them. But we're squaring all of that. Okay, so this is what we have. Notice now there's a common factor of magnitude of a squared, magnitude of b squared in both of these terms. If we factor that out, we'd be left with 1 minus cosine squared here, which from the Pythagorean identity in trigonometry we know is equal to sine squared. So we have the magnitude of a cross b squared equals this entire expression squared, taking square roots of both sides, and then there's a little observation that's important here, but taking the square roots of both sides would almost get us to this. But we have one important thing that we have to recognize. When you take square roots of both sides of an equation, you're supposed to put a plus or minus, right? Now, the left-hand side of this equation here is a magnitude of a vector. It cannot be negative. So that implies that this right-hand side needs to be positive as well. However, remember this condition. Theta is supposed to be between 0 and pi. That's the first and second quadrants. And sine is already positive in the first and second quadrants. So the plus or minus there is unnecessary because this side is already guaranteed to be positive anyways. We have no conflict between the sign of those two sides of the equation. And that gives us that equation that we wanted to prove. Okay. Now this has a corollary. A corollary is an immediate result of a theorem. We just proved this theorem up here relating the magnitude of a cross product to the magnitudes of each vector and the angle between them. If two vectors are parallel, A and B, if A and B happen to be parallel, then think about what that would mean here. Two vectors are parallel if theta is either equal to 0, that would imply that A and B point the same direction, or if theta is equal to pi, or 180 degrees, that would imply that they point in opposite directions. Both cases are accounting for A and B being parallel. But whether theta is equal to 0 or pi, sine of both of those values is equal to 0. So that would imply that the magnitude of two parallel vectors, the magnitude of A cross B is equal to the scalar 0. However, only one vector has a magnitude of 0, and that's the 0 vector. Okay? So what this is saying is, and we proved one direction of this thing, if and only if proofs require a proof in both directions, but the argument we just made basically establishes this. If A and B happen to be parallel, then A cross B is going to be the 0 vector, and vice versa. Okay? All right. I'm going to go ahead and do this in the next video.